Hello, ladies and gentlemen. I hope everyone is doing well today. Today we are taking a look at limiting reactants Chemquest. So to start off, we have some information on limiting reactants. Before we take a look at that information, I want to provide you guys with an example. Like always, we're going to try to relate this to some food. Makes it easy to remember. So let's relate it to making a peanut butter and jelly sandwich. So if we relate this back to our reactions, we could say we have some amount of peanut butter and jelly with some bread, and then we can make peanut butter and jelly sandwiches. So this time though, we're going to add something new into it: excess reactant and limiting reactant. So if we take a look at these pictures, you can see we have tons and tons of peanut butter and jelly. We have lots of it. We only have 2 pieces of bread. It doesn't matter how much peanut butter and jelly we have, because we only have 2 pieces of bread. We can only make 1 peanut butter and jelly sandwich. So this highlights what the excess reactant is and the limiting reactant is. The excess reactant is going to be the reactant that you have too much of, that you can't use all of it. You're going to have leftover at the end of the reaction. Your limiting reactant limits your reaction. You only have so much of it, and you're going to run out. You can only make as much peanut butter and jelly sandwich as much bread you have. You can only make as much product as much reactant you have. So let's take a look at this reaction now. So remember, guys, our definitions are down here. Limiting reactant, it's going to be totally consumed before the other reactant, therefore stopping the reaction. Our excess reactant, it's called excess reactant because there's going to be some left over at the end of the reaction. So let's take a look at our example of propane right up here. Our example of propane. So again, we have 1 mole of propane reacting with 5 moles of oxygen, forming 3 moles of carbon dioxide and 4 moles of water. So we see that's a 1:5 ratio because we use the coefficients of propane to oxygen. So again, if you had 10 moles of propane, you could burn the 50 moles of oxygen according to the reaction. But again, if you only had 20 moles of oxygen and 10 moles of propane, you wouldn't be able to burn all of it. You wouldn't be able to complete that combustion reaction. Therefore, this reaction would have been limited by the amount of oxygen you have. So therefore, oxygen would have been the limiting reactant. So now that we kind of understand a little bit about what excess reactants are and limiting reactants are, we're going to take what we learned and be able to do some calculations to be able to determine which reactant is which type. When we are working on these calculations, we are going to be using mole ratios, which we learned about in the last Chemquest. Remember, the number of moles is equal to the coefficients in the balanced reaction. Remember, if you only know the mass in grams, you are going to have to convert to moles, so we can use the mole ratio. Remember, it's called the mole ratio, not the gram ratio. So now let's scroll down. We can go down to question 1. Oh, and as we're solving these, we are going to round to 2 decimal places. So in the above discussion, it was evident that 20 moles of oxygen isn't sufficient to combust 10 moles of propane because we compared it to the coefficients, 1:5 ratio. So then, how many moles of propane would be able to be combusted if we had 20 moles of oxygen? So remember, guys, what you're going to notice here is it's asking us for moles of propane, and we only know moles of oxygen. So, this is going to tell us it's a mole-to-mole conversion because, again, we have moles. So we're going to be using the mole ratio, and we're going to be using our balanced reaction up top. So we start by setting up our T. So we put 20 moles of oxygen, 20 moles of O2. If we want our moles of O2 to cancel, we put them on the bottom. And then if we want to convert to moles of propane, we put that on the top. Moles of propane, C3H8. Remember, guys, propane formula is C3H8. So now we go back and we use our coefficients. 1 mole of propane, 5 moles of oxygen. So that's how we fill the numbers in. We put a 1 next to moles of propane, 5 next to moles of oxygen. Once you solve this, you find that the answer is 4.00 moles of propane. Remember, include the zeros because I did ask you to round to 2 decimal places. So then next, it's asking us how many moles of carbon dioxide will be produced. So we do need to base our answer off of the amount of propane that will actually be used. We can't start with the 10 moles of propane that it said we had because we're not going to be able to use all of that. So that would be like saying we can make like 20 peanut butter and jelly sandwiches because we have this much peanut butter and jelly without knowing how much bread we had. So we can't really say that. So we need to base our answer off of the amount of propane we actually have. So again, we start our calculation by setting up our T. We want to convert our moles of propane C3H8, so we put that in the top left. Next, if we want our moles of C3H8 to cancel our moles of propane, we've got to put them on the bottom. Now it wants us to convert to moles of carbon dioxide, CO2, so we put that on top. We notice here that we have moles and moles, so this is a mole ratio problem. So then we use our coefficients. We have 3 moles of carbon dioxide, 1 mole of propane. So we put a 1 next to C3H8. We put a 3 next to moles of CO2. When we solve this, we get 12.00 moles of CO2. Now we can move on to the last one, part C. So part C is now telling us if we have 12.5 moles of propane and 63.2 moles of oxygen, then what is the limiting reactant and what is the excess reactant? Well, it tells us that propane is the limiting and oxygen is the excess, and we need to explain why. So what we need to do here is we need to take one of these. We need to either take our moles of propane or our moles of oxygen and convert to moles of the other reactant to see how much we actually will use and then be able to compare. Because remember, these numbers right here, the 12.5 and the 63.2, this is how much you actually have. This is the actual amount of each reactant. So we need to actually now take and say if we actually have this much propane, how much oxygen will we actually need? Theoretically, how much are we going to use in the reaction, not how much we actually have. So let's take our 12.5 moles of propane, and now we can convert to moles of oxygen to be able to compare, to be able to say if we have this much propane, this is how much oxygen we need, and then we can compare it to how much we actually have. So we put our moles of propane on the bottom, our moles of oxygen on the top. We see that it's a mole-to-mole conversion, so we go back up and we look at our coefficients. 1 mole of propane, 5 moles of oxygen. So we put a 5 next to moles of O2. We put a 1 next to moles of C3H8. Once we solve this, we see that there's 62.5 moles of O2. So this is, theoretically, this number right here, this 62.5, this is how much oxygen you actually need if you have 12.5 moles of propane. So then we can come over here and we can take a look. We can say we need 62.5 moles of O2. Do we have enough? Yes, we actually are starting with 63.2 moles of oxygen and we only need 62.5. So then you would see there would be extra left over. We have more oxygen than we need. So that is why oxygen is the excess reactant and propane is the limiting reactant, which is said right here. Propane is the limiting reactant, oxygen is the excess reactant. Remember, propane is the limiting reactant because we're going to use all of it. If we use 12.5 moles of propane, then we're going to have to use 62.5 moles of O2. So there, what we see here is there is leftover O2, so that means we're going to use all of the propane. So remember 62.5, we compared this number, 62.5, we compared it to 63.2 moles of O2. There would be leftover excess O2. And then if oxygen is the excess reactant, that means propane must be the limiting. So next we can go on to question 2. So question 2 right now, question 2 is giving us a new reaction, and it's telling us that we have 0.75 moles of MgCl2, magnesium chloride, the first reactant, and we have 0.65 moles of sodium phosphate, the second reactant. It's telling us that we need to verify right now. Verify that sodium phosphate is the excess reactant and magnesium chloride is the limiting reactant. So we are going to do this the same way as we did it in the other problem. We need to take the moles of one of the reactant, convert it to moles of the second reactant, and then compare. Because remember this number, the 0.75 moles of MgCl2 and the 0.65 moles of sodium phosphate, remember those are the actual amounts. That's actually how much we have of each product to work with, and we need to make sure we do some calculations to make sure that we actually have enough to complete these reactions. So we're going to take, let's just start with the left side. So we'll take our 0.75 moles of magnesium chloride, and now we can convert. If we want to convert to moles of sodium phosphate, we need to cancel out our moles of magnesium chloride by putting it on the bottom, and then we put our moles of sodium phosphate on the top. Now we can use the balance reaction to plug our numbers in, our coefficients in, our number of moles. So then we have 3 moles of magnesium chloride, so we put a 3 next to MgCl2. Then we have 2 moles of sodium phosphate, so we put a 2 next to moles of Na3PO4. Once you solve this, you find that there's 0.50 moles of Na3PO4. Remember, this is theoretically how much you need. So what you see here is to react with 0.75 moles of magnesium chloride, you need 0.50 moles of sodium phosphate. So what we know is this is the excess reactant, because you have 0.65. You're going to have extra left over. Excess reactant because you only need 0.50 moles and have 0.65 moles. So remember, this is the excess reactant because we only need 0.50 moles, but we have 0.65 moles to start with. So that means we're going to have some left over. In part B, it asks us to calculate how much excess we have left over. So we can calculate the excess by subtracting. So we know we're going to start with 0.65. We're only going to use 0.5. So then we can subtract to find what's missing. So we have 0.65 minus 0.50, meaning left over there would be 0.15 moles of Na3PO4. In part C, so part C, I don't want to scroll up that far so we can still see the reaction. So part C, it's asking us how many moles of sodium chloride NaCl will be produced. So remember, just like in our peanut butter and jelly sandwich, we need to make our calculation from the limiting reactant. It doesn't make sense to say we can make this many peanut butter and jelly sandwiches because we have this much peanut butter and jelly, because we only have enough bread to make one sandwich. So over here, it only makes sense to make our calculation from the limiting reactant, because if we made it from the excess, we have extra left over. We would be taking into account this leftover part that we can't actually use because we don't have enough magnesium chloride to react with this much Na3PO4 that's left over. So we need to make our calculation from the limiting reactant. So that's why we pick magnesium chloride. So we take our 0.75 moles of magnesium chloride and we set up our T. If we want our moles of magnesium chloride to cancel, we put them on the bottom. And then because we want to convert to moles of NaCl, we put them on the top. Now we can go back to our balanced reaction to plug in our number of moles, our coefficients. So magnesium chloride is 3, so there's 3 moles. And then we take a look and we see NaCl is 6. Once you solve this, you should find that there are 1.5 moles of NaCl. Not moles. Cancel. Likewise, if it asks you to convert to grams of a product, now you could convert our 1.5 moles of NaCl to grams if we wanted by using our periodic table. Alright guys, the last question I'm going to go over is question 3, parts A through D. Afterwards, I am going to ask you guys to complete the last question, question 4. Question 4 is all the steps are modeled the same way as I am doing in 3A through D, so you're going to have to model your problem after how I solve question 3. So guys, I do realize as I was solving this problem out on my own that there really isn't enough room on this paper, so you are going to have to do this on a separate piece of paper. There are several blank pages throughout the packet. You can use one of those, or you can just do it on on a separate piece of paper, and then we can staple it in during class. Alright, so guys, the first part of the question, it asks us to write the balanced chemical reaction for the reaction between calcium sulfate and sodium iodide. So this is part A. This is the first thing that we are going to do. Write the balanced chemical reaction. So we have our reaction between calcium sulfate and sodium iodide. It tells that up here. So remember, this is a double replacement reaction, so we need to switch based on the charges. Remember, to get these charges I used the periodic table. So we know that based on these charges that calcium and sodium will trade places because they're both positive. So that means sodium will be where calcium is bound to sulfate. Remember, when you combine, make sure you crisscross your charges. So sodium has a positive 1 charge, sulfate has a -2. So then we crisscross. So then the first product is Na2SO4. Then we do the same thing. Calcium will go where sodium is, so it will be bound to iodine. Remember to crisscross the charges. Calcium has a +2, iodine has a -1, so we crisscross. So the formula becomes CaI2. Now we need to go through and balance. So we double check. We make sure we have the same number of atoms on the left side as the right side. So we double check. There's 1 calcium on the left, 1 calcium on the right. So far so good. This is sulfate. So remember, there's no parentheses, so that tells us there's 1 sulfate on the left. Again, there's 1 sulfate on the right, no parentheses. Now we check our sodiums. There's 1 sodium on the left. Because of subscript, there's 2 on the right. So that means we need to ask ourselves, what coefficient do we add? We need to multiply. What times 1 gives us 2? The answer is 2. So we put a 2 in front of our sodium iodide. Next, we check the iodines. Because we added this 2 here, we would do 2 times 1, meaning there's 2 iodines on the left. And then we look and we see there's 2 iodines on the right. So now we know this is the balanced reaction. We can rewrite this just to make it a little bit easier for us to read. CaSO4 plus 2 NaI goes to Na2SO4 plus CaI2. And that is going to be the balanced reaction that we're using for the rest of this problem. So then next, part B. Part B says find the limiting reactant, and then it lists out a few steps which I'm going to go through. So the first things we need to do is convert our grams to moles. Remember, we're going to use the mole ratio, not the gram ratio, so we need to be in grams. To convert to grams, remember, we're going to need the masses from the periodic table. So that's what these are, all of the masses from each of the reactants and products. Remember, if you solve this by adding up the different masses from the different elements on the periodic table. So to convert to grams, the first thing you need to do is set up your T. When we set up our T, we're going to put what we're starting with in the top left corner. So that's what you see I did right here. All I did was read the problem. The problem tells us we have 37.4 grams of calcium sulfate and 58.3 grams of sodium iodide. So that's where I got those numbers from reading the problem. So then next, if we want our grams of calcium sulfate to cancel, we put them on the bottom. And then if we want to convert to moles, we put moles on the top. Now we go through and we plug our numbers in. Remember, if we're using a mass from the periodic table, it's 1 mole, and then that equals the mass that's on the periodic table. For in CaSO4's case, I was able to calculate it was 136. When you type this into your calculator, you find that the answer is 0.26 moles of calcium sulfate. Next, we do the same thing for sodium iodide. If we want our grams of sodium iodide to cancel, we put them on the bottom, and then we can put our moles of sodium iodide on the top. Oh, sorry, it's just a little out of focus. So then, just like before, we took our mass from the periodic table, so that means it's 1 mole. And then the mass we calculate on the periodic table goes next to grams, 150. When you solve this, you find that the answer is 0.39 moles of sodium iodide. So since these number of moles were calculated from the amount of grams that we were starting with, these are the actual number of moles that we are working with. So this is the actual number of moles we have. So then to calculate the limiting reactant, what we need to do is we need to do what we did before. We need to take one of the moles and calculate to see if I have 0.26 moles of calcium sulfate, how many moles of sodium iodide would I need? We do that by doing our mole conversion, converting our moles of calcium sulfate to moles of sodium iodide, and then comparing. So we take our 0.26 moles of calcium sulfate, and now we're going to do our mole conversion. So if we want to cancel our moles of calcium sulfate, we put them on the bottom. And then if we want to convert to moles of sodium iodide, we put them on top. Now we used our balance coefficients. So we'll check it out. Remember, the coefficients equal the number of moles. So that 2 moles of sodium iodide. So that means we put a 2 next to moles of sodium iodide. Next, we check moles of calcium sulfate. There's no coefficient there, so it's a 1. So then when you type this into your calculator, we find that it is 0.58 moles of sodium iodide. So right here, this number, 0.58, so that is theoretically how much NaI, sodium iodide, we need to react with 0.26 moles of calcium sulfate. So what we need to do is then compare to the actual amount of sodium iodide. The actual amount was what we calculated earlier in part B. So we actually need to have 0.39 moles of sodium iodide, but we need to have 0.58 moles. So what this tells us is we are going to run out of sodium iodide before we have the 0.58 moles necessary to react with the 0.26 moles of calcium sulfate. So we are limited by the amount of sodium iodide that we have. So then what that tells us is NaI, sodium iodide, is the limiting reactant. So that means throughout this problem, we need to be basing all of our calculations off of the number of moles of sodium iodide, because we can't be basing it off of the one that we're going to have extra left over of. We need to base it off of the least amount we have, just like with the peanut butter and jelly sandwiches. We can only make one sandwich because we only have 2 slices of bread. So now we can continue this problem. So part C is asking us to use the number of moles to calculate the number of moles of the limiting reactant to calculate the number of moles of each product. So that is what you are going to see me be doing right here. So I am going to leave, I did it on a separate piece of paper so I can leave up the reaction and some of the masses that will be important in part D. So if we want to calculate moles of our products, remember we need to start with the moles of the limiting reactant. So I did it in 2 separate different T's because we have to do it for both products. So we'll do it for the first product, sodium sulfate, first. So if we want our moles of sodium iodide to cancel, we put them in the bottom. And then if we want to convert to moles of sodium sulfate, we put them in the top. Remember, when it's a mole-to-mole ratio, the coefficients equal the number of moles. So we have 2 moles of sodium iodide, so we put a 2 next to NaI. We have 1 mole of sodium sulfate. Remember, when no number is written, it's a 1. Once you solve this and we round to 2 decimal places, it comes to 0.20 moles of sodium sulfate. We do the same thing for the next reactant, calcium iodide. So again, if we want our moles of sodium iodide to cancel, we put them on the bottom. And then we put our moles of calcium iodide on the top if we want to convert to them. So again, we use the coefficients. 2 moles of sodium iodide, so we put a 2 next to NaI. 1 mole of CaI2, so we put a 1 next to calcium iodide. Again, when you type this in your calculator and solve, you get 0.20 moles of calcium iodide. Part D then asks us to convert from moles to grams to figure out how much of each product we have. So then that's what you're going to see me do right here. I'm going to take the moles of what I calculated in part C, and now I'm going to convert them to grams. So if we want our moles to cancel, we put our moles on the bottom, moles of sodium sulfate, and then we put our grams of sodium sulfate on the top. Next, remember, so this is why we calculated all the masses in part B, is because now we have our grams of sodium sulfate. So we can put our 142 next to the grams, and then a 1 next to the mole. When you solve this, you find that you have 28.40 grams of sodium sulfate. Then the second one, we do the same thing. If we want our moles of calcium iodide to cancel, we put them in the bottom. And then we put our grams of calcium iodide in the top. Again, in part B, we already calculated all of the masses that we need. So again, we have 294 grams of calcium iodide. 294. And then we put a 1 next to the mole. Just like this. Then, when we type this into our calculator, we find that the answer is 58.80 grams of CaI2. So guys, that is how I solve 3A through D. So, what you guys need to do right now, I gotta find it, I put it right here. So number 4. So number 4, you guys need to solve number 4 and base your work off of how I modeled it on 3A, A through D. It is the same steps, you just need to apply it to a different reaction. Like always, guys, if you get stuck, tell me where you got stuck, write down a question, don't just tell me you got stuck. I'll see you guys next class. Hope everyone has a wonderful day. Bye.